Yeah, so thank you for the introduction, and then this is going to be my last lecture. I hope. So I'm talking about higher periphase, and then I move on to higher dimensions. It's all going to be higher, and then usually I lose people if I go.
The problem with that is when you fall.
That's right. That's right. Yes. Okay. So today is about entanglement. So here's the quick recap once again. So this is the inner product for 3 matrix product state, and then 4 2D state. But now I'm moving to this diagram. We have a 8 state, but we are not going to talk about something related to topology. We are going to discuss something more like quantum entanglement. And then since I'm using the multi-wave function overlap, as I said something in the introduction, it is related to multipartite entanglement. So we are going to discuss entanglement part. So for the simplest example of multipartite entanglement could be these states. So for bipartite entanglement, we have a Bell pair, EPL pair. But for example, if you go to the 3 qubits, you can have interesting entanglement pattern, which does not exist in the 2 qubit system. So there's this GHZW cat state, or there's also something called W state. And as it turns out, for this setting, setting of 3 qubits, there's the 2 class of tripartite entanglement which are distinct. So for example, this paper classify all possible ways 3 qubits can entangle with each other, and then these are 2 classes which are distinct from Bell pairs. But this is still in the few body setting. So we may be interested in multipartite entanglement in the quantum many body physics setting. Okay. So this is going to be my talk today. And then as a particular quantum many body state, we are going to discuss topologically ordered phases. So I think we had a lot about topologically ordered phases already. So I guess I don't have to really mention any basics, but anyway, this is the strongly correlated 2+1D systems where we have interesting excitations, anionic excitations, and they have a non-trivial statistics, fusions, and then they're encoded or summarized in the data, topological data. So that defines topological order. Okay, so we are going to study tripartite entanglement in this class of quantum many-body systems. So to speak about entanglement in topological systems, the natural starting point is the topological entanglement entropy for bipartition. So we have we start with the pure state, ground state, on the 2D, let's say, plane, and I just bipartition the plane into 2 regions. Then I think one way to introduce topological entanglement is to look at the subleading contribution to the leading area law contribution to the entanglement entropy of subregion A. So this number, minus log D, captures the universal information of topologically ordered state. It's related to something called total quantum dimensions. So we heard about quantum dimensions yesterday, and then this is like a sum of all quantum dimensions of anyons in this space. And then this has been measured, people may not like to call this measured, but it has been used in quantum devices to diagnose topological order. On the more conventional experimental, condensed matter experimental side, there have been a lot of progress in detecting topological order. For example, braiding statistics has been measured, and then I'm going to talk about something which is related to this chiral central charge or central charge, which is another important ingredient to characterize topological order.
This was also measured.
Yeah, yeah.
In your list, these are all theory papers, right?
No, this is perhaps, this is the...
This is a multi-Heitman?
Yeah, yeah, I think so. So,
So even in the
yeah.
integer Hall effect,
Yes, integer for, yeah, that's right, that's it. There's just even, yeah, that's right.
was
Yeah.
earlier.
There's area, that's right.
For C equals 1.
That's right, exactly, yeah, yeah.
Actually was 6.
That has been measured, yes.
The
So,
transport is unidirectional.
that's right. So, yeah, idea is to list something measured here. Yeah, yeah, that's right. So, but the problem is that just in terms of these characteristics, data, we cannot fully distinguish different topological states of matter. For example, if you're just looking at the total quantum dimensions, it is the smoking gun of topological order, but it cannot distinguish, for example, the toric code topological order and then Ising topological order. So we may need more, we need a finer probe to distinguish different types of topological order. So I'm going to use multipartite entanglement as an attempt to go beyond bipartition topological entanglement entropy. Okay, so that is the motivation. So then what we are going to do, as yesterday, is to tripartite this 2D space-time in this region ABC, and then these three regions, they meet at a point here, which is like a tri-junction. And then what kind of entanglement properties we can study and detect in this setting. So that is the today's talk. So I'm going to use the terminology of mixed state quantum entanglement, which is very closely related to multipartite entanglement. So I may go back and forth between these two perspectives. So idea is that if I start from a pure state supported on region ABC, then you can trace out region C to get a mixed state on AB. And then you can study the property of the mixed quantum state on AB. Okay, so you can, there's some ways to diagnose the quantum correlations in the mixed state. That is typically more difficult than discussing entanglement in pure state. So this is like quantum correlation or entanglement in the mixed state. But we can use some tools to study mixed state entanglement to say something about multipartite entanglement of the original state rho ABC. Okay, I mean this is just a perspective, and then we may go back and forth between these two perspectives. Okay, any questions so far? Good.
I mean, you could have also studied the case where A and B are not actually are embedded in C, but they are not neighbors, so they are physically.
That's right. So that's the tripartite. Yeah. So this is particular tripartition, and other tripartition have been studied before. So I'm not mentioning these earlier works, and then they capture different things. Yes.
So what can you? It's a question. What is the difference between this case where A and B are disjoint, or this case where they share a boundary?
So the point is that, for example, I think perhaps you have an A, B, and C in between, and A and B are separate. In that case, I don't think it's completely trivial, but I think mostly you can focus your calculation between A and B, and then B and C separately. And then there's some like a global constraint, maybe it's because of the Wilson loop or something like that. But that case is, I would say, somewhat more easier. I mean, I did that type of calculation with, for example, Schroeder-Wen some time ago. But this case is a bit trickier because these three meet here. So that's a new aspect. Okay. Are there other questions? Okay. So let me first introduce the this multi-entropy. I perhaps mentioned this earlier. So it is represented by this diagram. Okay, oh, I lost. Yeah, here. I put the labels here. That was when we are discussing something like a Berry phase, because I need to take a different state. But in studying entanglement, I don't need these labels. So you should think of these as the exact identical copies. Okay. So formally, this quantity multi-entropy is defined in this way. So I take 4 copies of state, and then these operators here basically specifying how I connect these different legs, okay? But I guess equation, rather than equations, maybe this diagram is just more intuitive. Another way to think about this diagram or this equation is to first consider these pairs, psi and psi, and one of these is bra and the other is ket, as specified by this arrow. And then these vertical bonds are the degrees of freedom representing region C. So if I connect psi 1 and psi 2 by this leg C, I'm tracing out region C. So this pair can be considered as a reduced density matrix on region AB, okay? So I have a 4 reduced density matrix here, 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 because I trace out these vertical bonds. I'm tracing out region C. So in terms of the reduced density matrix, this diagram is equivalent to this diagram. Each row is like a psi bra psi ket. But now I have to connect this reduced density matrix in a very funny way. Okay, so this is how we define this multi-entropy. Yeah, question?
So the 1, 3, 5, 7 on the top, are these different spatial regions here, or where?
Oh, so they are just representing different copies. So this, yeah, this diagram, yeah. So this diagram does not have any spatial information anymore. Yeah. Does that make sense? Yeah. Partial, yeah, I'm doing partial overlaps, but these states are all identical. That's the difference. Yeah. Yeah, question?
The psi?
Yes. Psi.
You put psi to the 4, psi.
That's right. So that simply means I take 4 copies here. So these are like a ket, and then it's a sum state. Okay. And then I take another 4 copies. Let's say they're sitting on the bottom. They're like, yeah, maybe I should put bracket notation. But so these are kets. I have another ket, but they have a 3 legs. I'm connecting them.
So the pi operators tells you how they are glued together.
That's right. So they're using this permutation operator notation, which is more convenient if we discuss generic version. So this is like a one particular multi-entropy, but there's a series of quantities you can construct this way. I don't think you want to hear about the definition of the more general version because it's rather complicated, but this is the simplest one. And then these quantities are introduced in these papers. And then I think there's some motivation from more like holography and so on and so forth. But today we are going to use this idea to study topological states of matter. Okay. I hope the definition of this quantity is clear. And then I will say a bit more about what kind of things we can know from these quantities later, but this is first just a definition.
So your notation,
Yeah.
you have H22R of A colon B. What does A colon B mean?
Here.
Yeah.
Okay. Let me move on. So
Well, this is notation.
this is notation. So we just introduced this quantities. And then I'm also I'm going to introduce yet another quantity which is called reflected entropy. And then as it turns out, this quantity is related to any version of reflected entropy. So I'm going to the next slide where we introduce this quantity. Okay. In fact, yeah, so from the way I'm presenting here, it's more natural to introduce multi-entropy first because I'm using this multi-wave function overlap. But historically, this reflected entropy was introduced before, so it's actually perhaps natural to introduce reflected entropy before. But I'm going to do this in the next slide. But just before doing this, it is also, I'm going to consider this particular combination. So I define this quantity GABC here using this diagram, but I subtract these second Renyi entropy for region A, B, and C. Okay, this has a this will somehow, in some sense, in analogy to topological entanglement, we can cancel the area row type terms, and then this is a convenient contribution. And then I'm dropping all these index A, B, C, just call it kappa because I'm only using particular setup. Okay. Okay. So what is this S? Okay. So S is related quantities, and it's called the reflected entropy. And then, sorry, this is a busy slide, but it is defined in the following way. So once again, I am discussing the mixed state. I started with pure state, but let me now use the language of mixed state after tracing out C. So I have a mixed state supported on region AB. And then one may wonder, is there any interesting quantum correlations or let's say entanglement in this mixed state? So this reflected entropy is somehow measure this correlations in the mixed state, and it's defined through this canonical purification. So what is a canonical purification? So it is the pure state which somehow corresponds to this mixed state, but it is defined in a bigger Hilbert space. So my Hilbert space initially is HA tensor HP, but you double the degrees of freedom, so you have now copies of A and then B here. So it's a bigger Hilbert space, and then you define pure state in a bigger Hilbert space. Okay? In a simple term, you just flip this bra to ket. So that's what you, okay, I have to also do some coefficient change here, but that's basically what you do here. And then this state is constructed such that if you take the partial trace over this A and B, A star and B star, these are the fictitious Hilbert space. Now I go back, I reproduce mixed state. Okay, so you write mixed state as a pure state, but the price you have to pay is that you have to enlarge your Hilbert space. So it's called canonical purification. So if you trace out A star, B star, you go back to the mixed state, but instead of doing this, you can trace out B and B star here, and you are left with some state on A star. Okay? So from there, you can define a reflected entropy as a von Neumann entropy of rho on A star. So that's the definition of reflected entropy. And then in the next slide, I say something about the usefulness of these quantities. But let me move on to a few other kind of formal things. So like this quantity kappa I introduced here, I'm going to consider this quantity H, which is the reflected entropy minus mutual information. Okay, this turns out to be also good quantity to consider, which cancel the area row term or other terms. And then this one, you can show that this is always non-negative. And then it is known under the name of the Markov gap from the quantum information perspective. So I'm going to focus on these two quantities, kappa in the previous slide, and this quantity H. Okay, right. And then once again, this quantum information quantity is introduced by energy physicist Faulkner, and then data And then one of the motivation was that they have a very nice, this quantity has a very nice holographic dual description. And then I also introduced the Lenny version. I mentioned the Lenny version in the previous slide, which is defined. This is like a von Neumann version, but you can also consider the Lenny version of this quantity using in this way. So von Neumann entanglement entropy has a log in the expression, and you want to write it as a powers of density matrix. Also, I have some power 1 over power 1/2 here, which you can also modify. So by changing the power here, you define the Lenny version of diffracted entropy, which depends on 2 Lenny indices, M and N. Okay, so this is the way to connect this multi-entropy. Yes.
Rho to the m isn't the density matrix. What do you mean by the purification? Is it rho to the m over 2 acting on times the identity acting on the maximum mixed state?
This one? Yeah. So this one is the purification of this one.
But that's not a density matrix.
Yeah, so we properly normalize. Yeah. So it took like a trace of this is 1, and then so yeah, you have to normalize, but then you can make this look like a proper state, then you can purify. Yeah, sorry, maybe I have to put the normalization. Thank you for the question. Yes.
This nice holographic dual, you mean the wedge cross section?
Yes, this is related to something called entanglement wedge cross section.
It was settled that this is the quantity that is measuring, because there is also this version by Takayanagi.
That's right.
They do something similar, but minimize overall possible.
That's right. So I think it is more or less settled, or I mean, in physicist term, I think it's established that this is dual to entanglement wedge, but there are other quantities which it's not mentioning here, but they're connected to entanglement wedge cross sections, and then what is called the it's also related to canonical purification, and I forgot his name. Sorry, it's like an entanglement of canonical purification or something like that. And then there's also something called the odd entropy, and then negativity may not be related to entanglement wedge cross section, but initially I thought it may be related. But there are other quantities, various other quantities. From the they have yeah.
Several quantities give the same result in holographic.
So for some of these quantities, calculation is rather complicated. So that was the part of the confusion. For example, negativity was initially considered to be maybe related to entanglement wedge cross section. By that I mean we thought it may be related, but these quantities are defined not in terms of von Neumann entropy, but it involves some powers like a Lenny type index. Then there may be replica symmetry breaking and something like that. And then that was a complication. So however, for example, for negativity, there's a recent result by my past student, Jonah Kudra from, and then collaborators. They sort of clarified this aspect. So they look different. Calculation look very different, in fact, and then but somewhat more complicated. But this is the simplest one where you can do very nice calculation, and the holographic dual is clear. Yeah, and then other questions? Okay, and then I think, but from the perspective of many body state, the quantum informations, somehow they share the same motivations. We want to understand the correlations, quantum part of the correlations in the mixed quantum state, and then perhaps the multipartite entanglement. Okay, and then maybe I should also say, if you look at the qubit literature, there are many quantities proposed to diagnose the multipartite entanglement like hyperdeterminant, tango, and so on and so forth. I'm just using these quantities because they are useful for many-body quantum systems, okay? Because some of the quantities in quantum information literature is not very easy to compute or formulate in a many-body quantum context, but these are the kind of quantities which may be less understood from the quantum information perspectives, but nevertheless we can calculate and then in the many-body quantum physics context. Okay, maybe I should move on to the next slide because we are going to starting to discuss the motivation. So what this reflected entropy tells us? That is the question. And then, so yeah, it's less understood, I guess, for multi-entropy. So here I limit myself to the reflected entropies, okay? So first of all, we can discuss what is a reflected entropy. What does it tell us in the few qubits, few body context? And if you, for example, look at the GHZ state and then W state, this H, which is the reflected entropy minus mutual information, they have, they take different values. So that is the indication that reflected entropy may be sensitive to particular kinds of tripartite entanglement, so it may be useful to distinguish different kinds of tripartite entanglement.
Have different symmetry properties also.
Yeah, yeah.
So in some sense, this is sensitive to symmetry?
I think there's a way to think about entanglement using symmetry, and then
I mean, for instance, the W state is an eigenstate of the chiral.
Yes, that's right.
Whereas the other is invariant under Z2.
Z2, yes. So, yeah, so they certainly have a different symmetry pattern, and then I think there's formulations where we try to understand the entanglement using what happens if you act symmetries, or if you act on the symmetry on qubit A, what happens to the other qubits, and then how symmetry action on A is translated into other qubits, and so on and so forth. So I think this is perhaps a very useful way to think about it. But today, I think I don't have much to say about it. Yes. Okay, so this is nice first indication. I think this paper from UC Berkeley group, they did quite a lot of progress on this direction. So this paper further show that for one-dimensional, essentially for one-dimensional gapped system, H is 0 if and only if the state is gapped, okay? If I break down this statement a little bit more, they first show that this H is 0 if and only if the state is fall into the class of state, what they call the sum of triangle state. That is the generalized version of a GHZ state for many qubits and many products of local Hilbert space. So that's called sum of triangle state. I don't write down the expression, but they identify a class of state, okay? And then for this state, H is 0, and then conversely, if H is 0, the state must be sum of triangle state, okay? Also, it is also in the 1+1D many-body physics context, if you take a matrix product state representation, and if you coarse grain it a lot, eventually we float to the fixed point of the matrix product state. It's like RG, okay? And then at the fixed point, matrix product state takes this the form sum of a triangle state. Okay, I lost here. Okay, and therefore we conclude that 1D gapped systems has H equal to 0, and if H is equal to 0, the state is gapped. A question? Yes.
Are you saying that? So you're saying that the fixed point H is 0. Are you saying that if it's 0, then it's going to be 0?
Yeah. So either you make systems as big, or you change the size of this region. And then in a particular limit, it's, yeah, but we are only interested in the statement in the thermodynamic limit. Yeah. Yeah. So maybe convenient way to think about it. Instead of changing state, you fix the state, but just region is very big. Other questions? Yeah. So the next question is what happens if gap closes? So in the gapless regime, so it may be conformal field theory. They show that this is actually maybe shown before them in this paper by Faulkner and Data maybe, but anyway, in the gapless quantum critical chain, this quantity h takes a universal value, which is C/3 log 2. So this is after subtracting this mutual information part, and only the universal contribution remains. Okay, so this is I think at this stage this started to look like really the interesting quantity to look at. Okay, and then maybe it's not completely understand, but I think this is a very interesting quantity to study. Once again, much less is known for the multi-entropy, but nevertheless we can study these quantities. Okay. So the next thing I want to discuss is our main target. So that's a topological states of matter in 2 dimensions. Right, so this is I first present some result, okay, and then I will elaborate. But let me first present the result in the ideal cases, okay, ideal cases where we can do analytical calculations. I mean, I will summarize the overall result later, but this is some particular calculations I'm talking about. So in this paper, we studied topological liquids using the technique I discussed yesterday, the bulk boundary correspondence, and so on and so forth. And then we found these results. So H is, once again, C/3 log 2, so it looks identical to the 1D result. Yes. Yes, that's right. So it is going to be, it turns out to be that is the case. Yeah, maybe I should present that way, but here more like I'm following the historical development of so we first found this, but at that stage we didn't really realize it is which central charge we are discussing. But anyway, for example, if I take this particular image, let's say we did this calculation first for the chiral case, so we only have a chiral central charge, and then we get this result. We also study, okay, we didn't study explicitly the non-chiral case, but similar results should hold if I replace this C by the total central charge, okay? Anyway, this is the first result we found, and then similar results for kappa. For kappa, coefficient is slightly different, but main message is that this result is independent of the size of subregions, independent of the regularization or smearing coming from the bulk gap, and so on and so forth. So this is really like a universal part of the bipartition entanglement, which carries topological information. But the information which we detect here is different. It's a center charge. Okay, so this is the one result. In the another paper from the UC Berkeley group, they studied once again ideal model. In a sense, they took Levin-Wen models, and then they have a technique which is called isometric tensor network method. But they use this technique to calculate H analytically, and then they got H equal to 0, which is just the result for different cases. Okay.
So what is the meaning of H being 0 or not being 0? What does it tell us if H vanishes or doesn't?
Yeah, so I will tell you some conjecture. We are somehow correcting results, but you sort of see, it may be related to central charge here, but here central charge is it's 0, so it's a bit confusing, right? But I will tell you, I think. Question, yes.
This is just a random question. Why log 2 when we want to log 3? Or is there any intuition
Yeah. So yeah. I don't have an intuition, but I do know why this is log 2. So this log 2 comes from the OP coefficient of twist operators, which we have to compute. For example, this is log 2 because for the case relevant here, it's a twist operator of the Z2 orbifold. I don't say this is intuitive understanding, but origin is understood. That's right. Yeah. So G2 orbifold, and then yeah. So yeah. Okay. So I may be able to connect why to say something why it's G2, but I don't remember off the top of my head. But if you change Renyi index, you can get different twist, and then for some of the complicated twist, we don't know the OP coefficient, unfortunately. So we cannot write down the explicit form, but essentially this will just depend on the OP coefficient of the twist field. I will say something about twist field later, but that's the, I don't know, at least the mathematical origin of this formula. Okay, so this is result 1. I also want to present non-ideal models, which is lattice models, something like this. So this is not topologically ordered, but it's a non-interacting lattice model, fermion tight binding model, and then fermions are hopping on the square lattice. And then this model has not topologically ordered state, but the Chan insulator phase, which is sort of topological. So I have one parameter in this model here, U. So they change U. You can go from, let's say, topologically trivial phase, Chan number 0 phase. So yeah, this part is very large. Essentially, you can ignore hopping. This is just on-site term. So this is like a trivial state. But you can tune trivial state to the topologically non-trivial state through the critical point at here. Okay, so this is the in this case, we can just study these entanglement quantities numerically. So we try partition the square lattice in this way, and then we study how these entanglement quantities, reflected entropy and the multi-entropy, how do they behave? So we are going to discuss. And then for reflected entropy, we find, yeah, okay.
Is there something, okay, let's go back to the Chan insulator.
A Chan insulator, yeah.
Yeah. Okay, so in the first, in the topological phase, we have Chan number 1, okay, you have essentially a chiral
State, yes.
at the edge.
Yes.
So it should be like C equals 1.
C equals 1, yes, I should say that, yes.
So what happens at the critical point?
That is the reason why we wanted to do the numerics. Because our
For instance, sigma xy, the whole conductivity,
yes,
jumps from 1 to 0.
that's right.
But at the critical point is 1/2.
Yes. So that's right. So these yeah, exactly. So these methods are limited deep inside the gapped phase. But the reason we wanted to do this is one reason to do this is to test this formula, but another motivation for the numerics, that is numerics, we can look at critical point. Yes. So we are going to discuss a little bit. Yeah. Okay. So this is the result. Okay. Sorry. So if you plot H in this unit of log 2 and 3, C is 1. So this is properly normal is 1. So you don't see step, but it just changes continuously. And then there's an enhancement at critical point. But let me first focus on the gapped phase. So remember, from 0 to 2, I have a topological phase. And then beyond equal 2, I have a trivial phase. And here's a phase transition point. There's another phase transition point at 0. But anyway, so this is the topological region. So for anywhere, almost anywhere in this region, if I do this subtraction, H is independent of the subregion size and the system size. I mean, at least if you make them very big, so it's constant. So it is system size and subsystem size independent. Okay, but it's not exactly C over 3 log 2. But if you are deep inside this gapped phase, it is very close to C over 3 log 2. So here it's like almost like 2 times C over 3 log 2. But in the lattice geometry, because of periodic boundary condition, I have number of trijunction on this geometry is twice as large and the continuum. So the factor of 2 may be just explained by the number of trijunctions. But if you take into account that factor of 2, it's sort of like C over 3 log 2. Okay? And then there's also similar result, or even they have an even better result. But anyway, this is a result, and there are similar results for the multi-entropy. So once again, multi-entropy changes like this, and there's a small peak here near the phase transition point. If you pick particular point deep inside the topological region, this kappa quantity now is almost constant as a function of the sizes. And then this extrapolated value, it's almost constant anyway, but it's very close to this expected number. Okay? Yeah. Yeah, we didn't check very carefully, but here it's largely system size independent. So as if it's always system size independent, but only this value is different. Yeah, but we are not so sure if we are very close to the critical point. For example, this is slightly off the critical point, 1.999 to 0.000. Then yeah, you start to see the size dependence. So we are not able to say, you know, if you are very close here, if you make systems as big and big, eventually do this or it continue to do this. That we are ultimately not sure. But so it's the numerics. But yeah. Maybe yeah. I think that's
You mean it's a
scaling function. Yeah. That I'm not sure. Yeah, critical point is once again, you can sit exactly at the critical point. That's also.
Is that consistent with a cusp or a maximum?
This one. Yeah, we are not sure if it's really a cusp or does it. My student even thought there may be a sudden discontinuity here, but eventually, numerically, we are not able to say too much about it. Okay, so yeah, there's a critical point, near critical region. It's interesting to discuss on its own right, but let me focus on this this comparison with the analytical result once again. So yeah, analytically in the ideal limits, it's a constant, and then it is given super sharply defined this way. So collecting all these results, what is the overall picture? Okay, overall picture is this picture. So this is a conjecture. So yeah, let me focus on this quantity h. So the conjecture is that C over 3 log 2 is the bound, universal bound. So h should be always bigger than C over 3 log 2. So that is a conjecture. This UC Berkeley group phrased this conjecture in the following way. Sorry, I didn't also say another important part of the conjecture. So this is a bound, but C over 3 log 2 is a bound, but C sitting here is the total central charge, but it's a total central charge of ungappable degrees of freedom. Okay, so there's the topologically ordered state may or may not have a gapless edge state. Chiral state always have gapless edge state, but for the non-chiral state, like a toric code, edge state can be gapped. Okay, chiral central charge is 0. But even when the total even when the chiral central charge is 0, there are some systems where you cannot gap the edge state. Okay, so you just count the central charge, total central charge of the ungappable degrees of freedom. So that is the central charge sitting on the right-hand side of this bound. And then this can be just phrased as an inequality, but here it is written in terms of this minimization over U. So this is a U which you can act near, yeah, maybe I just don't have to go back, near the trijunction. So you start from some state, but you modify your state a little bit near the junction by short depth circuit, and then you can change this value of H, but you cannot go below C over 3 log 2 as far as there's the ungappable degrees of freedom. So the UC Berkeley group really tests this way. Although I think although they cannot do, maybe they did in some sense, but they cannot perhaps take all possible unitaries and test this conjecture, but they did numerically test that if you act with unitaries, you can reduce H, which is as if we are, moving in this way in this phase diagram. But as far as they test, within their test, they cannot go below this value. So this is perhaps the universal bound, and then we could set up similar conjecture for this kappa. So kappa, even for the kappa, maybe this C over 8 log 2 may be the universal bound. We did not. That's right. Yeah, but yeah, we did not. But I think similar things should happen. Yes. Okay. Any question about this statement? Yeah. So okay. So this is somewhat analogous in my mind. That maybe not entirely the same, but it's a bit like C theorem. If you float to the fixed point, which is deep inside the gapped region, it is really central charge. But if you are away from the ideal point, it may take different values, but it is always monotonically decreased toward the fixed point in the gapped phase. But that's a conjecture. So it's interesting to perhaps work on this type of statement, at least analytical or more fundamental understanding rather than just testing it. Okay. So yeah, usually to show something like irreversibility, we need, these what the Marina and Horacio did. Like you can use strong subadditivity or some, let's say, known inequality in the quantum information theory context, and then you can perhaps use that to say something about many-body physics context or quantum field theory. That is still lacking, but this conjecture may be attacked in that way. But right now I have no idea. Okay.
This H doesn't have any known monotonicity property.
Yes, so
Because it's a quantity of two regions that are touching each other, right?
yes. Yeah, so I'm not sure if there's a fundamental reason not to have any inequality, but yeah, I don't know any inequality on my side. And then there's also the related work by Patrick Hayden and then companies. They show that H is not monotone under LOCC. That's a quantum information theory operations. so many to be a proper entanglement measure, you want to have a quantity which always decrease as you do some local operations, because local operations cannot increase entanglement. And conversely, if you have a quantity which always decrease under local operation plus classical communication, that is considered to be entanglement measure. But I think H may not have that properties, at least for qubit systems. But we are discussing many-body systems and then quantum field theories. Maybe the hope is that it may be different from the few-body systems. But at this moment we don't know. And another comment I want to say is that this H may be obstruction to have a nice tensor network lattice representation. If H is non-zero, there may be an obstruction. For example, chiral state has this bound which is non-zero, and then that may somehow indicate that it may be more difficult to have a lattice PEPS representation of let's say chiral state. And then I'm mentioning this because practical level, we can use PEPS as demonstrated by, for example, the series of work by Paul Blanc and the companies. But I don't know, it's not a doubt, but I thought it may be interesting to look into multipartite entanglement in these chiral PEPs and then test if they can produce or if they agrees with these results. These PEPs may be good for just studying correlation functions or something like that, but if you look more into the detail of the state, there may be some differences. Okay. Okay, so that's about these two quantities, reflected entropy and the multi-entropies. And then I have a bit more kind of, not quite aside, but bonus for this. But is there any question for this?
In higher dimensions, is known something like that. This result for conformal field theories, for example, is not known. What happened?
That's right. So this you can compute by using holography, for example. But yet that's quantum field theory.
Sorry, there is a state that is morally equivalent to the toric code, which is the Poynter-Dimer state on the triangular lattice, which is in the topological phase. But there is a finite correlation there.
I see.
It's not a state with a vanishing correlation there.
I see.
So in that sense, it's not really in the topological limit, because there is some scale.
Yeah.
So presumably some of these violations will be present there and not in the toric code, which has a vanishing correlation.
Yes, toric code has zero central charge, but yeah, that's the, yeah, so that's a separate question. But yeah, of course we can study for these systems where correlation length is not zero. Yes, that's maybe.
So presumably they will not saturate this bound.
Not saturate this bound. Yeah. I think I do expect something like that. Yeah, question? Yes. Yes. So yeah, this is. For Laflin wave function. Yeah. I'm actually getting into this. That is. So ideal limit may be topologically capturing the Laflin state, but Laflin states have a lot of geometrical aspect. So that is actually the subject related to next. Yeah, that's actually a very good question. Okay, other questions? A question, yes. Yeah, I was confused about the inequality in which direction. Yeah, sorry, I have to go back. Yeah, so it's upper bound. Yes, it's upper bound. Yes. So the interpretation is SR capture some informations, but it's always overestimate information. Always overestimate the. Yeah. Yes.
These C over A and C over 3.
Yes.
Do you know what the mutual information is?
Yes, I will perhaps mention. So numerically, I don't know, but analytically, we computed both reflected entropy and the mutual information and the subtract. So I do know mutual information in this case, and that is going to be in fact the next slide. Yeah, but yeah, it's. Yeah, so we have to subtract. So that, but I want to discuss how it diverges. Yeah. Other questions? Okay, I was afraid yesterday that somebody may be going to ask that question.
Where's the Markov chain?
You know, it's related to Markov chain, and then it's. I learned this terminology once, but then I forgot. Sorry, but it was this paper by Hayden, Source, and then Onkar Parikar. That's one of the quantum information motivated terminology.
Maybe if H vanishes, then you can show that some conditional mutual information vanishes as well?
Yeah, maybe, but I'm too afraid to say something very inaccurate. Okay, other questions? Okay. So let's okay. So I have at least a few slides to say something about computation, and then computation is the same technology, and we went over this technology yesterday. So I don't spend too much time, but the idea is very similar. I use bulk boundary correspondence to write the ground state near the entangling boundary, and then do calculations. So then we connect these things here. Yesterday I had the less copies, just this and this, 4 wave functions. But now I have 8 wave functions and 4 reduced density matrix. So I have four reduced density matrix here. Okay, I'm not sure if you remember this terminal, the meaning of these diagrams, but you can see at least there are 4, and each represent reduced density matrix. And then we connect them, okay? And then in this case, as compared to the diagram from yesterday, this diagram is a bit more complicated. It's a genus 5 surface. But we study this quantity in some limit where I think these directions are very large in this particular limit. So we can actually do the calculation. Another way to look at this complicated surface, if you are familiar with the entanglement entropy calculation in field theory, we use replica trick, and then there's also the twist field formalism, twist operator formalism, and so on and so forth. So if I use a replica language using now the single theory with n copies sitting on a non-replicated manifold, this is the manifold I have to say. So here's the different perspective where I have a replicated space-time. Each has 1 copy. But this is now a one space-time, but on top of that, there's n theory living on top of it. And they're connected through this branch cut. Okay? And then this we can calculate using the twist operator formalism. In this particular limit, this diagram decomposes into the cylinder part, and then something in the central region, but something we know how to calculate. So that's how we get this result. Okay. So yeah, details I don't want to really mention it, but there's a bonus of this formalism, because using this formalism, we can study something called the corner contribution. So this is conceptually separate from the study of multipartite entanglement, but in studying this pizza slice partition, we create sort of sharp corner here. So this is now a bipartition setup, but now it has a very sharp corner. Okay? You can just think of, taking, instead of having A, B, and C, you declare C is actually the same as B. So that's a kind of special case of our calculation. So as a bonus of technique we're developing, we can actually compute the contribution to the bipartite entanglement, which depends on the angle. Okay, so this is the area law term. And then there's also the topological entanglement entropy part. But if you have a system with non-zero center charge, I think this is a chiral center charge, this part depends on the angle. And then this is the what we get from this calculation. Okay? And then this corner contribution, when I'm computing refracted entropy and the multi-entropy, they are there because of the shape of the junction. But once I consider the subtracted quantities H and kappa, these corner contributions, as well as the leading contributions, they all cancel, and we are left with this result.
So C is it's a chiral?
This is, I think this is chiral center charge.
In the previous transparency, you have like a sum of the two.
No, it's not? Okay. Maybe you're right. Okay, thank you for the comment. Yeah, so sorry, I said chiral center charge, but I think perhaps John is right. This is perhaps the total center charge. So.
I think it is.
Yeah.
I mean, with John Moore, we had a simple.
Yes, that's right. Yeah, that's right. It's a similar thing. Yes, that's right. It depends on the angle. And yeah, that's right. Yeah. Yeah. This numerics? In my numerics. So we are doing subtraction, but we are not paying too much attention. We just compute this box region and just doing maybe. That maybe, yes. Yeah, but okay. Maybe we didn't look into that question. Okay, so now we want to compare this with quantum Hall system, reference state. Maybe not reference state, but at least for the integer quantum Hall state. So this is what you did, in fact. So the comparison is in the next slide. Yeah, so this contribution has been studied. I think I'm comparing one of these numerics perhaps from here, but yes, you did most pioneering work. So the point is that my formula does not fully agree with the numerics. So this blue curve is the result. Center charge is 1 for the integer quantum Hall effect, and this is the curve we have. And then this red point is the numerics from this paper, I think. And there's other numerics, but let's focus on blue and red. And for if the angle is large, they agree. But if I go to the very sharp angle, they start to disagree. So I think we are still lacking some understanding of ultimately how my undat state in analytical communication is always this undat state. This is my undat state, but this state fails to model the state if I have a very sharp angle. So this is an open question.
You should also have some angle dependence that do not come from the boundary conformity that comes from inside, right? From the degrees of freedom at the corner, right? So
maybe, yes.
This particle will be also divergent, but it will also have a dependence on the angle.
Yeah, so you're saying this is not accurate state. This is a boundary state which doesn't have an angle. Yeah, that's maybe, yeah.
So you get an angle dependence from this finite piece that is kind of but then you also have some common.
That's right. Maybe both contributions. Yeah.
If you only see at the boundary dependence, the angle dependence, they mix up. Right?
Maybe that's maybe true. That's maybe true. Yes.
That's what I was
Okay.
There's a nice scheme to subtract that.
Oh, there is. Okay. Maybe I'd like to know. Yes. Okay. So this is kind of maybe not from the. I'm going backward. Not for the interest of multipartite entanglement, but it's more like just bipartite entanglement, but that may be linked to more detailed understanding of topological liquid beyond just topological properties. Sometimes people may phrase this as a geometrical contributions. And then, personally, I want to understand it a bit better. But at this moment, this is the analytical result we have. Okay, so almost finally, I just want to link to many other known things. But before mentioning related works, I want to make some terminology straight. So I will going to talk about various results related to central charges, but there's a few types of central charges we need to discuss. So we already discussed the chiral central charge, and then there's also the total central charge, but it makes sense to focus only on the ungappable part of the central charge. So this is the total ungappable central charge, okay? So some result depends on the chiral central charge, the other depends on this total central charge. Chiral central charge is almost just independent data for the theory of anion, except if you consider the chiral central charge mod 8, so if you exponentiate, there's some known relation to the data of anion statistics and fusion. So this is D, once again, is the quantum dimension of anions. Theta is like a statistical angle or spin of anions. And then this particular combination is known to be related to the chiral central charge. In thermal transport, we don't talk about mod 8. It's just chiral central charge. But the mod 8 part of the chiral central charge is somehow topological. There's also something called higher central charge. So once again, we go higher, higher, higher. But this is, you change the power here, you define something analogous to this object, and this is called higher central charge. And this is relatively recently proposed quantity, and then there's a nice, maybe mathematicians, but there's a nice physics work which relates this higher central charge to the gappability of the edge state. Okay, so these are the quantities I want to say something about it. So first, these multi-partition ideas have been, I think, started to be used more widely to study topological liquid, in particular something like a central charge. I focused on the reflected entropy and but multi-entropy, but there are some more results along this direction. So, for example, there's something called the modular commutator, which is defined in first of all, they consider this region ABC, but unlike my setup here, this region is a part of the system, part of the let's say 2D plane. So in some sense, it's like a tetrapartition. So you focus on this region ABC and outside, but within this region ABC, you consider reduced density matrix for this disk, and then KAB is the entanglement Hamiltonian for reduced density matrix AB and the BC, and you take a commutator. Okay, so this is called the modular commutator, and then these papers show that this modular commutator is related to the chiral central charge. Okay, so this is another nice result. I think it's not directly related, but I think it's sort of similar. It extracts slightly different data because it's a chiral central charge. And then this partitioning is also slightly different. And the reflected entropy, I think I already mentioned. Multi-entropy I also mentioned. Interesting recent work from Israel is that you can study multi-entropy not in this setup, but using this tetrapartition. And then they show that the multi-entropy in this tetrapartition setup does extract this higher central charge. Okay, I think that's also another related interesting result. And then there's a lot more result, which is, yeah, maybe it's diverging, but there's a lot of result I just want to mention. So there's a lot of related work from John on the entanglement bootstrap approach, and then there's also the relation to the extraction of the central charge and even the Virasoro algebra from the wave function of topological liquid. Central charge has been extracted from the topological ground state, maybe not by using the idea of entanglement, but there's something called the momentum polarization, which can capture the central charge from the wave function. So starting from here, it started to be slightly different from what we talked about, but I think it's nevertheless related. Generalizing some of along this line, I had a paper which in which we can extract higher central charge using the similar idea as momentum polarization. We just call it partial rotation, but we can extract higher central charge using slightly different scheme. And then there's the central charge as some sort of response to the fractional quantum Hall liquid. So this has been slightly back, but there's the many works along these directions. And then, yeah, so this center charge, and then gravitational anomalies, and then geometrical response have been developing into a very rich field. Okay, so that's almost the end of my, I think, slide. And this is the whole summary for the 3 days. So thank you for having me for 3 days, always in the morning. And then I got a lot of feedback, so thank you very much for your attention. Yes.
Just a comment. If you have the mutual related to what I was talking yesterday, if you have these high-value violations for two intervals, you can see if you have the mutual information, you have the usual diversions when they approach. But you also have an additional constant term. It's kind of topological. It's called an index. It's just a number. I wonder if you have that situation, the two quantities that you are subtracting, the reflected entropy and the neutral information, yeah, both of them have the same number, or we will change the result of C over 3, just as a comment on.
No, I think it's quite related. So for the reflected entropy, it turns out to be super universal if you do this subtraction. It's always C over 3 log 2. Maybe it's not completely related to what you're saying, but for example, I could do the similar subtraction for negativity or something like that. In that case, we do cancel the divergence, but constant is not super universal. So I don't really understand, but it's maybe it's related to what you're saying. Yeah. So Renyi 1/2, yeah. That's right, Renyi 1/2 for, yeah. So maybe connecting to what you're saying, in some cases, maybe it's not defined as an index. Maybe for this case, it can be understood as an index. That could be explain why it's so stable, but
No. I mean, the C over 3 log 2, that's kind of not an index because it depends on C.
Oh, okay, so that's not the index. I see.
In that sense, it's kind of an index that measures the central charge, so it's kind of strange.
I see.
Right? It's a constant thing, but
that's right.
But it could be that this quantity also measures this index or not. I don't know. That's my question. But
yeah, that I'm not sure.
It's an additional term, right? On top of the central charge term.
Additional term on top of central charge. That I'm not sure. So yeah, in some sense, numerically we do subtraction. So we sort of seeing it, but we couldn't find any good Okay.
What does it mean that H is 0? So for instance, if it is related to whether the H states are gapped or not.
Yeah, H state, so yeah, conjecture is if H is 0, you have a gappable edge. That's the.
For instance, if you take the toric Hall, the H state may or may not be.
Yeah, so, but it's, yeah.
So there is a particular point where so the H is critical.
That's right. So the claim is that this state can have a gapless edge, but it's gappable. So that means you can similar thing can happen at the junction. So if you make a particular trijunction, you may see a lot of correlations there. But there's a fine-tuned case, so you can, act with some small unitary circuit here, then you may be able to remove this contribution, then you can go. So it's precisely like what you're saying. So for the edge, you can go to the critical point, but in this particular, you can also go away from the critical point. Yeah, so that is what is measuring.
But is there any monotonicity expected? I mean, I know
Yeah.
the early attempts of finding an extension of the C theorem
Uh-huh.
beyond 1+1 dimensions.
Uh-huh.
One of the things that people did, myself included, was to look at essentially the behavior of the entropy in the field theory at the critical point, the larger limit you can compute,
Uh-huh.
and it's not monotonic.
Yeah.
There are to actually do something monotonic, you have to do it like what you did.
Yeah, so
It's different.
No, it would be very nice, and I think it's not correct that this quantity, as two intervals are attached to each other, would be monotonic with the size, because in that case you have already the C theorem, because you enlarge and enlarge, and then you get something like that, right?
Right, but
Already.
the case otherwise
So without
is more like
the-
a thermodynamic property, which is not necessarily monotonic. Okay, so it's
yeah, at this moment I don't know, but it would be very nice to have some progress in the. So maybe first Hermann, and then maybe, yeah.
Has some of these ideas applied to the entanglement aerosol systems? I mean, you have a symmetry, in one symmetry, then you can,
Ah,
right? And then you can measure the level of SO2, for instance. So in principle, we could apply some of these ideas, right?
so yeah, you can also include symmetry, and then, yeah, that's a very interesting direction. I didn't do that myself, but for example, this modular commutator idea here, they did include U1 symmetry. So in that case, they can extract something like quantized whole conductance. But yeah, I think including symmetry seems to be a very fruitful directions. Yes, and then maybe first Fiona, and then Paul.
maybe it should go down.
You know, you talked a lot about what is looking for entanglement measures that you have essentially the chiral charge. So what if I have an SPT? Is there a way to
Yeah,
so with symmetry it has an edge that cannot be gapped, but the edge is technically gapped.
that's right. That's right.
Do you have any thoughts on whether a similar
That's a good question. Yeah, short answer is I haven't thought about that, but yeah, once again, maybe incorporate symmetry and maybe SPTs, maybe very fruitful directions. Yeah, Paul? Yeah.
You know, I want to re-ask something that I think has more or less been asked multiple times, but maybe phrase it more bluntly. The reason we look at, well, it's some intuition from control field here. The reason we look at corner terms and things like that is because the coefficients are supposed to be universal, right? Nothing else, it's dimensionless, nothing else depends on angle like that, so the coefficient has to be universal. It's not